Hello everyone. In this class, we'll continue with the drawing operations. In previous videos, I have explained you the design calculations or even the basic calculation of calculating humidity, percent relative humidity, given the data on uh, mm, partial pressures or pressure fractions, right? So based on that, we have calculated. Now also I have shown you the humid volume and enthalpy calculation also. Now, to make the work easier in the design operations, we use something called a psychometric chart, which is a chart representing dBT, WBT, and many other properties of air in a single graph sheet. So if you need any information, you need to refer that chart, and all the data are available directly. So let's go ahead and see what is this psychometric chart, or so called as humidity chart now. So this particular chart, let us go ahead and see and uh, check out, learn it with the numerical. Here we are. Now this is a psychrometric chart. We can also call it as a humidity chart. Usually psychrometric chart is a technical term used for general gas with any molecule associated with it, like a moisture. Specifically for air and moisture case, we mention it, call it as humidity chart. So humidity chart, it includes properties of air such as dBT, WBT, dew point, specific humidity, relative humidity, it is percentage, specific enthalpy, specific volume. All this information are present in a single graph, and they are generalized into a single graph sheet. Something looks like this, right? This is the outline sketch, a schematic sketch how a humidity chart looks like. Here you have a dBT line on the x-axis. It increases in this line. In a while I'll show you the actual humidity chart. Before that, let me tell you what are the different components in it first. So it's a dBT line, dry bulb temperature line, and you have a thick line over here, right? Similarly, a curvature you can see on the temperature, you can see later. So that is the wet bulb temperature line. In fact, that itself is the dew point value is also mentioned on that. So it will be a slant line, something like this. Okay, so it will be a slant line. um, then you have values on enthalpy, one char line, humidity ratio, and humidity, relative humidity. Relative humidities are curves almost parallel to this 12 temperature lines. Then humidity ratio is the y-axis over here, and you have specific volumes lines coming over here, and maybe at the bottom you can get that values, those things. Now the key point over here in the entire calculation point, you should be able to identify one point on the graph sheet. To identify one point among this, all right, among this information, WBT, dBT, enthalpy, relative humidity, humidity ratio, specific volume, of this, these are the properties of air. Of this, any two values should be known to you. If you know any two values, you can identify exact one point. Usually experimentally we can find out dBT and WBT. These two are experimentally you can identify it. So usually all the cases dBT and WBTs are mentioned. Given these two information, you can draw the line and get a point. Given the point, you can find out the remaining information. How we do it, let us check it out. Normally the wet bulb temperatures are varying in a temperature scale, normally in degree Celsius. dBT will be in degree Celsius, and humidity ratio H, that will be in the scale of gram per kg, gram moisture per kg air. Then specific volume will be in the unit of meter cube per kg, enthalpy kilojoule per kg, all are kg dry air. On a kg dry air basis, all the values will be mentioned. Relative humidity will be in a percentage scale, moving towards this way, okay, moving upward like this. It will be moving this order. Now let me show you the actual humidity chart before I explain you how to use it. Alright, here we are. This is a representative humidity chart. This is one graph representing humidity chart for almost a majority of the temperature ranges. So this is the dBT, dry bulb temperature, starting from minus 20 degrees Celsius till 60 degrees Celsius here. And this curvature line here, okay, starting from about minus 20 degrees Celsius up to, it goes up here 30 degrees Celsius, right? So 30, 40, up to 30 or 35 degrees Celsius it goes on. Yes, values are written here. and this inclined lines, what is coming down over here, right, written 20%, 30%, 40, 50 like this, these lines are percent relative humidity. And the humidity lines over here, this is the line on one side of it, the left side of it, it is the humidity ratio, it's in gram moisture per kilogram of dry air. The values are over here 10, 20, 25, 30. These are the values representing humidity. On the right side of it, it is a vapor pressure data. This one 2, 3, 4 up to 34. These are vapor pressure data. It's in mmHg scale. On the extreme right, you have the enthalpy of the mixture, and on the top over here also you have the enthalpy. All right. Uh, then the saturation temperature, that is a dew point also over here, which we can see based on whether data is available or not. Now this particular line at the bottom, you have the specific volume. So the specific volume of the dry air, this is the line, inclined line in the negative slope. Those are the humid volume. All right. So this is how it looks like. Just to zoom in, how it looks like. Right, so you have the dry bulb temperature over here, you have the percent relative humidity, right, these lines, and the specific volume over this line, and these are dBT values 15, 20, 25. You have the enthalpy values over here, and you have the humidity ratio H 10, 20, 25, these values, and on the right side of it you have the vapor pressure data. On the extreme right you have the enthalpy values again coming into picture. All right, yeah, this is how a humidity chart looks like. Now let's go ahead with the calculation on how we use it for our analysis. All right, here when you use humidity chart, note that we have already solved a problem number 10 and 11, in which the humidity, all those values were given, and we calculated it, right, in especially in problem number 10 where humidity was used. Those values can be obtained from this humidity chart. Given the humidity chart, given dBT, WBT, you can evaluate all the unknown terms, and you can use that for energy balance and mass balance calculations. All right, now this is how we do it. This is the generic way of getting a value. So generic way means the dBT value. So steps are written here, it's readable. So step 1 we go ahead with the dBT. Step 2 we take up dBT value, right, these two are known to us. So intersection point, so this is the dBT line, sorry, this is the WBT line, red color is the WBT line, wet bulb temperature, and the green colored one is the dBT line, dry bulb temperature line. So intersection point is this black dot, identify that, move horizontally, straight line, move horizontally till you see the humidity value. That particular value is the humidity, that is gram moisture per kg dry air. And if you move, if you look at the line, inclined line, percent RH, identify one line that passes through the point of intersection. Sometimes the point of intersection may be on the upper side or lower side of that one line, so a given line may not be passing through, but you can see that the adjacent to it, the two percentages, means for example if it is falling in between two different percentages, we can take an averaged way calculation and check it out. And if you extend that line, you get the enthalpy and this volume over here. So the line which passes through that intersection point, that is the specific volume. So that is how you can calculate the different properties of air. So let us solve one problem for just as an example. There are three cases. You can refer through the notes, but I'll explain only one for time being. 12A, 12B and C, a similar one but with a different property you can calculate. Now in this case, the dry bulb temperature is 30 degrees Celsius, wet bulb temperature is 25 degrees Celsius. So the dBT is 30 degrees Celsius, this is 30 degree, so make a straight line. Then WBT is 25 degrees Celsius over here, make a inclined line, just follow that line, a line is passing through that, right, so you pass through that, you get an intersection point. Now this intersection point you have to move horizontal over here, this is the value, and if you refer to that value, it will be 18 gram moisture per kg dry air. So this is the absolute humidity. Now if you want to find out the percent RH, so the percent RH over here, So if you look at it, 60% line is below the point and 70% line is above the line. What you can do is you can use a scale ruler and find out what fraction is on 70% side, what fraction is on 60% side, right? So the percent RH is in between 60 to 70. You just have to calculate how much distance it is fractionally, how much fractionally it is away from 60. That much you have to add. For example, the difference between on this line, on this WBT line, if you use a scale, measuring scale, the distance between 60% to 70% over there is 1 centimeter. 60 to 70 is 1 centimeter, and the distance between the 60 to this point of intersection is zero point 0.6 centimeter. All right, so total is 1 centimeter distance between 60% to 70%. Distance between the 60% to the point of intersection is 0.6 centimeter. That means from 60%, this intersection point is 60% away before 70, right? So the point of intersection is away from 60%, that is 60% RH, by a value of 60%, that is 0.6 out of 1. So that means you have to add that extra, that 60%. The difference is 10%, right? 60% to 70% is 10% gap. So it is 6. So it comes out to be 6. So the percent relative humidity is 60 plus 6. That extra 6 it has gone, right? So 66% is the relative humidity. So approximately you will have to identify. Similarly, you can identify the enthalpy. You can identify the molar volume. Then given the other way around, so if you are given with the humidity value and dBT, humidity you can get one line, dBT you can get one line. So point of intersection is known, you can calculate any other values. This point of intersection is a very key point. Identify that using any one of the property of air on the graph. Then given the intersection point, you can calculate rest of the unknown values. Now for this class, that's it. Thank you.